And now it's time for Arto Annila of the University of Helsinki. I understand that there is a video of him. I don't know who is going to upload the video. I think it's Christine or maybe Ram.
Christine will
About the
do it.
origin of ubiquitous patterns.
I appreciate having this opportunity to give a talk at the International Conference on Thermodynamics 2.0. You are listening to a pre-recorded talk to avoid eventual technical problems with an online presentation. Also, due to the time zone difference, I would prefer receiving questions and comments per email for me to address them in a few hours. In line with the profound objectives of the ICT 2.0, I see science as a way of making sense of the world rather than being merely an enterprise for modeling data. This is to say, science is not so much of spotting a trend in data, but explaining why the data looks as it does. When it comes to data, it is an astonishing fact that all data look essentially the same when displayed without units of access and labels. For instance, the length of words vary like the length of genes, the strength of earthquakes vary like those of the impulses in the brain, innovations spread like epidemics. The same ubiquitous patterns are found everywhere. In larger and larger areas, there are more and more animal and plant species. For example, small islets serve as a habitat to but a few birds, whereas larger islands are home to many more species of birds. Likewise, the number of vocations increases as the economy develops across time. For example, technological progress has created digital carriers. Moreover, when zooming in the depths of the night sky with a powerful telescope, galaxies pass by at a similar relative frequency to the junctions when driving on a highway. In the center of a cluster of galaxies, neighbors are close to each other. In the suburbs, road crossings are near one another. At the edges of the cluster, as in trackless wilderness, there is a lot more space. Yet another example of this grand regularity is the branching of a nerve cell, which is similar to the branching of a tree. The trunk forks here and there, while the branching quickens and ends in many leaves at the top. The distribution of branch length from the base to the ends is skewed in a universal manner. The units and scales vary from system to system, yet, regardless of the source, the form is ubiquitous. Irrespective of scale and scope, the data follow mostly power laws. That is to say, data points are mostly on straight lines on log plots. Even chaotic motions result in the same pattern over time, as minor events take place often, whereas major ones seldom. Also, spirals display the same form, only in polar coordinates. To be more precise than the first-order approximation by the power law, data, both spatial and temporal, follow sigmoidal curves on linear plots. These are cumulative curves of skewed, nearly log-normal distributions. Random, symmetric distributions, Gaussian curves, are found only in textbooks. As Gabriel Lippmann said, everyone believes in the normal law, the experimenters because they imagine that it's a mathematical theorem, and the mathematicians because they think it's an experimental fact. This Luxembourgian physicist reminded us that repetition makes things familiar. Soon the familiar notion is taken as the truth, while it may not be true, merely a convention. The world is statistical, yet nature's statistics are not the random variation of the normal distribution, but the regularity of skewed distributions. So, what is the causal law from which the grand regularity follows? Mathematically speaking, what is the law of nature that underlies the statistical law of large numbers and the central limit theorem? Jacobus Kapteyn was looking for the answer. In 1903, the Dutch astronomer, who had an interest also in biology, asked, "What is the reason for the widespread occurrence of this log normal curve?" The regularity found in datasets is salient, but does it hold good in reality? What if the grand regularity is only a figment of our imagination? Surely the pervasive patterns and the similar shapes in themselves mean nothing and prove even less. We do not have to agree about the significance of the grand regularity, for unanimity is not the goal of science. The truth is, as the philosopher of science Karl Popper pointed out, the growth of knowledge depends entirely upon disagreement. We can debate, for example, how similar the datasets really are, as we tend to think that a law of nature means a course of events without alternatives. However, the world does not seem to be deterministic, or for that matter, indeterministic. Random processes lead nowhere, and therefore deliver symmetrical distributions, whereas natural processes produce skewed distributions. The universality of data suggests that there is a profound principle, a law of nature. Admittedly, it may seem strange that the law of nature could describe regular yet unique processes. We tend to think that small deviations in data are due to random fluctuations or measurement errors. But the variation is not random, but it has its causes, however small and momentary. Since neither determinism nor indeterminism explains the universality of the patterns, we must look for a non-deterministic, unpredictable, yet causal law that accounts for historical contingency. According to such a law, there would be no random deviations from an average, so to say, from the ideal course of events, but all courses of events would be relevant because even the slightest consequence has its cause. Galileo's method, in which one's own experience is mathematized in a general law, seems to yield physics that is firmly related to reality. Hence, let us use it to find the law of causality and its axiomatic basis by structuring our experience of time into mathematical form. Let us look for meaningful explanations rather than intellectual challenges. Let us rely on common sense rather than established theories when interpreting observations. When we construct a theory in this way, there is a certain familiarity and unquestioned confidence. An effective theory in turn only models data, whereas a true theory explains the causal relationships that underlie the data. Moreover, a malleable mathematical model cannot be falsified, as it can be tinkered with pliable parameters, whereas a proper theory is not based on data, but an axiom that can be falsified with data. The ancient Greeks were masters in theorizing. In fact, the word theory originates from Greek, where it meant viewing, considering, examining, rather than, say, predicting. So we are after a perspective, a point of view from which the universality of data, the grand regularity makes sense, explain the world in which we live, the reality we face. It was a grand idea by the ancient Greeks, most notably Parmenides, Thales, and Anaximander, to consider that everything is ultimately made of the same fundamental constituent known as the atomos, literally undividable. Later, the term was ascribed to atoms, which proved to be divisible further down to elementary particles. In turn, the question of the ultimate composition of the elementary particles was addressed by an American physicist and chemist, Gilbert Lewis, who reasoned that everything must composed of quanta of light, which he renamed as photons. In practice, Lewis' thesis about photons as the fundamental element was not seen as convincing. Namely, the total number of photons did not seem to be constant. Specifically, an atom may go from an excited state down to the ground state either directly by emitting only one photon, or via intermediate states by emitting one photon at each stage. Since the number of detected photons depends on the route taken, it looked as if the photons appeared out of nothing and disappeared into nothingness. So it became a truth of physics that the photon could not be the indissoluble element. However, it is time to reconsider the photon as the fundamental element, because the nothingness, that is the void, the vacuum, space, must be a substance of some kind after all. Its spectrum, the Planck's law of radiation, reveals that the vacuum has a structure. Namely, the spectrum is not random, but given by the Bose-Einstein statistics, which can be understood so that the vacuum comprises trains of photons paired in an out-of-phase manner. These photons we do not see, only those single ones that are distributed among these trains, because the paired photons do not have electromagnetic characteristics that would couple them with matter electromagnetically. As Bose wrote to Einstein, to account for the Planck's law of radiation, it is enough to assume that the ultimate elementary region in the phase space has the content of Planck's constant h in each 3 dimensions. This revelation reverts the familiar equation from E equals h multiplied by F to h equals energy multiplied with time, which means that h, the Planck constant, is the measure of the photon, so that the photon is, after all, the undividable permanent element that has energy on its period. This perspective provides us with insight into the foundations of thermodynamics. Now we see that irreversibility follows from the fact that energy carried by photons invariably flows downhill. That is, energy differences always decrease, never increase. All processes are destined toward the balance where free energy vanishes and entropy is at the maximum. Moreover, since photons carry energy on their period, we understand that the flow of time is the flow of photons. This means that the photon period is the element of time. The concrete comprehension of time immediately makes it clear that energy differences diminish in the least time, as quanta flow along the steepest gradients of energy. If you like, you could say, with the words of Darwin, that the quanta naturally select the least time paths. Conversely, when there are no efflux or influx, the system is stable as quanta circulate on and on. So, at the steady state, there is no time evolution, only the phase of circulation advances. With this comprehension of the photon as the carrier of time and energy, Lewis postulates that the photons make up everything seems reasonable after all. Of course, we would still need to know how particles such as an electron comprises of the quanta of light. At this talk, I will provide you only a glimpse to this theme by reminding that an electron and a positron annihilate to mere photons. The two of them are readily visible, whereas most are in pairs, and thus we cannot see them. They remain undetected by electromagnetic means. Since such an out-of-phase pair displays no electromagnetic force. So, how do the electron and positron then look like? I will not go into it now, but I only remind you that first André-Marie Ampère and later Alfred Parson and then Arthur Compton considered that electron could be a torus, say torus made of photons. Of course, you have been taught that electron is a point-like particle. However, the researchers who carried out the investigations on the structure of electron concluded from their measurements if the electron is a composite particle, its constituents are strongly bound, giving the electron the observed point-like quality at experimentally accessible energies. So, the constituents of electron, the quanta in their tight coil, are strongly bound to one another like the strongly bound quarks. The main point is that we cannot present compelling evidence against Lewis' postulate that everything, particles just as the space, ultimately comprise nothing but photons. This axiom is central to us, as it was for Boltzmann and Gibbs for developing statistical mechanics. However, now we are competent to advance the formulation for open systems that enjoy a net influx of photons or a net efflux of photons. The key point is that if everything is made up of the same basic constituents, we may construct an energy level diagram that is valid for any system, since all systems are essentially the same, as they all are at the rock bottom, made of photons. I usually think of the energy level diagram in terms of a chemical reaction mixture. Molecules of increasing complexity are occupying the energy levels. These molecules are results of chemical reactions that have already taken place. So, in a sense, we have the diagram, which is a snapshot of the system undergoing chemical reactions. A moment later, some photons couple from the surrounding, say from the sun, to some reactions and drive the formation of compounds, while other photons emerge from reactions as molecules degrade down to their constituents. All this can be cast in a mathematical form using the standard procedure of statistical mechanics. The key concept is probability. Let us consider any one molecule indexed with J. For it to exist, there must have been ingredients, and there must have been photons that drove its synthesis. The number of ingredients, Nk, and their difference in energy relative to product J dictates the probability of J to exist, as well as energy carried by photons that must match the energy difference between the product J and the ingredient K. This simple formula is the most important. In fact, what follows is just mathematical derivation, which per definition does not change anything. Let us consider the probability of an array of identical molecules. It is simply the product over the single molecules divided by the factorial of Nj, because the order of identical molecules makes no difference. Finally, we obtain the probability for the whole system as the product of the probabilities of all species in the system. Next, we will move from statistical mechanics to thermodynamics by taking the logarithm of the probability to obtain entropy. It comprises two terms. There is the familiar Nk by T, which stands for the energy that is bound in the molecules. And there is the other, which displays the energy differences that are non-zero, unless the system is already at the state of balance. So these free energy terms drive the evolution of the system toward balance. Boltzmann and Gibbs missed deriving these terms as they focused on the equilibrium thermodynamics. The role of energy differences is clear when we take the time derivative of the entropy to C that the increase of entropy is driven by decreasing free energy. As a result of these reactions, the population change, the rate of change depends on mechanisms, for example, on available catalysts. While this description in terms of quanta is the accurate one, it is convenient to look at the motion as if it were continuous. For example, a flow of water seems smooth, although the stream comprises of single water molecules. The equation for continuous motion is obtained from the definition of chemical potential and likewise from the potential that the radiation is associated, say vector potential. And so we obtain the continuous flow equation. It is easy for you to recognize that at a steady state where dissipation vanishes, the kinetic energy 2K is at balance with the scalar potential U. This is often referred to as the virial theorem. For example, stars move in their own gravitational potential. Of course, they also sense the gravity of the expanding universe. Finally, we shall analyze the discrete equation to derive the ubiquitous patterns. The characteristic S-shape of the growth curve can be seen to result from the equation for the population changes. In the beginning, there is a wealth of resources, that is, free energy for growth, so we can assume that mechanisms limit the consumption of free energy and define the change in the populations using the forms for the chemical potentials and radiation to have no explicit but only stoichiometric dependence on Nj. The growth by the obtained equation is approximately exponential because initially the amount of free energy seems infinite. In turn, when the free energy dwindles down toward the balance, the growth decreases slowly, almost exponentially. We see that the growth between the initial and final exponential phases follows a power law closely by expressing Nj as the product of the basic element N1 and using the atomistic axiom, where the constant can be defined as a product over all transformations. Contains the free energy terms that force the assembly from Nj from N1. So the change, when integrated, follows a power law. The power law in the continuous form, that is to say, a derivative of the logarithm of the momentum equals change in the logarithm of the velocity plus the change in the logarithm of mass, is apparent from the Newton's second law of motion when divided by momentum. When the assumption of a nearly constant change in free energy does not hold, we may model the change adding a term in the equation of rate change, beta multiplied with Nj, where the population at time point t0 determines the population at a later time t. According to this model, evolution is almost predictable when the change in free energy is small compared with average energy, and when not, oscillations and chaos occur, for example when a solid-state laser is turned on, or when the animal population proliferates and exceeds the carrying capacity of its environment, or when the banks need more money than is available. Logarithmic, exponential, and truncated distributions and their power law-like cumulative distribution functions are mathematical models of the physical processes given by these equations. The models allows us to describe and categorize various data, but they do not explain how the data came about. That is causality. It's worth emphasizing that the equations from cannot be solved except at the balance. because the variables cannot be separated. It means that a chain of events is fundamentally unpredictable, not due to the complexity of the system or ambiguity in its initial conditions, but due to mutual dependencies. When the system evolves gradually, the change in energy is small compared with the average energy, and then the variation is small around a representative mean or an average factor. So the natural distribution of factors given in logarithmic terms of the elemental factor is approximately logarithmic. The typical form can be recognized in each member within the distribution. For example, all sized northern pikes look like pike and not bream, for example. On the other hand, if the weights of the pike and, say, cars were presented in the same graph, we would see two distributions, one about a typical pike and the other about an average car. Spiral forms of nature, such as shells, cyclones, and galaxies, are also approximately log-normal distributions, that is, energetically optimal shapes, but in polar coordinates. In summary, statistical physics of open systems, the thermodynamic theory of time explains processes as flows of quanta. As the quanta carry both energy and time, the irreversible consumption of free energy sets the arrow of time. The correspondence between the theory and data implies that every process seeks thermodynamic balance in the least time. Therefore, the patterns in data are ubiquitous. The maxim of least time free energy consumption is inherent in the quantum itself. Planck constant H equals ET as the product of energy and time determines the change in energy over time, that is, the power, as a motion with velocity in the direction of the force. This is to say, while the photon measured by Planck constant is indeed undividable, atomos, as the Greeks said, it contains change in itself. As the energy of the photon decreases, its period increases, so that the product always remains constant, the Planck constant. Thank you for your attention. I would appreciate receiving your comments and questions by email. Some answers you may find also from my homepage. Thank you for your interest.
Well, thanks everybody for your attention. I think we have had a very interesting day. Maybe Ram, or one of the organizers, want to say something now?
Actually, like we designed the Q&A session for next 15 minutes, but looks like we already taken care of Q&A from some of the speaker earlier. Therefore, I still like to open this floor for question and answer if there is any. I'm sorry that I don't think the Arto is here to answer directly, but as he have indicated, if you can file that question on the chat room, then we'll probably reach out to him and probably find the answer, and the other people will also benefit from that question. Yeah, our colleague Christine has put email for Arto in the chat room, and that's where his question should direct it to.
Ram, if I can make a comment, I suppose I think it was Terence's presentation where Dilip was asking whether he thought that information is more fundamental than matter. If I can make a comment on that, I know certainly information is physical, and the bit is, some scientists have argued that the bit is actually the irreducible kernel in the universe, and it's actually even more fundamental than matter itself. For example, to produce motion or change requires energy, whereas to actually direct this change, you need information. So one can argue that information is even more fundamental than matter and energy itself, if you look at it from that point of view. That's just a comment. Obviously, it's open to debate, but certainly it's something to think about.
That's really great.
I had a brief comment to that, and that is that, of course, there are, you know, as many definitions of information as you could imagine. Certainly information in the sense used by the it for bits, the it from bit group, is referring to information that has no reference, has no significance, has no function when we use the term information in our colloquial talk. Or in biology, for example, we're talking about something that represents something for something that has some use.
Yes.
That certainly would not be the use of the concept of bit by physicists, by James, for example, others who have used that concept. So I think the point is that there's a sense of information, and I like to equate it with the concept of constraint or symmetry breaking relationship that is universal in physics, and it's relevant to information theory as well. But it's not sufficient to talk about the information in our exchange, for example.
Yes. Yes, I agree. I agree.
So my interest was, in fact, to go at the biological concept of information.
That's really great, and thank you for Wasim bringing that up. That reminded me of this when we started thinking about the thermodynamics too. We consider there could be a three-thread, one based on energy, the second one based upon entropy, and the third one based upon information. And it was initially like that on our website, but I'm just sharing you kind of making of Thermodynamics 2.0. One of our board of directors strictly objected to that concept, but we didn't talk about what kind of information he was referring to, but he said that he was referring to the Shannon type of information. Mm-hmm. And I had so much respect with him. I'm sure he's listening now. So he even emailed me that if information is on the thermodynamics too, he will not be helping me on this organizing this conference. Therefore, we dropped that out. And he's listening now, and he might comment on that. But that's really great. We brought that up. And thank you so much, Wasim. And that reminded me of that making of thermodynamics too. I thought I'll just share you.
There's some very interesting problems surrounding, you know, information, thermodynamics, entropy, energy, and their interrelationship. There's no question that there's a lot of open and very interesting problems there.
That's really.
I'll make a few comments if on the topic. If people want to hear, as most people probably, Gerald Nahum knows, Terrence Deacon knows that I don't. The association of the equivalence of entropy and information is a fool's gold, as far as I'm concerned. And as far as about at least a dozen other, 2 or 3, if you're a solid physicist or a thermodynamicist, you know that, for example, when the famous Mandelbrot, famously said that everybody knows Shannon's derivation is an error, and that's just common. It's common. It's not. A lot of people like to think of it as a quick way to get into thermodynamics. And if you look at the journal Entropy, it's become basically a mess of confused ideas about mixing Prigogine entropy, Shannon entropy, Boltzmann entropy, Gibbs entropy, and it's produced more confusion than is needed. So I told Ram if he's going to do a thermodynamics conference, because thermodynamics textbooks are not based on bits. It's not a bit is not a fundamental. It's not an SI unit. So the conference needs to be based on SI units: energy, volume, temperature, pressure, which are the basic language of thermodynamics. And if you introduce thermodynamics, or if you introduce information into as trying to sell it as a fundamental unit in thermodynamics, the whole conference would turn into just a big mess within the course of 10 years.
I'd like to add something.
Along the same lines, if I may comment, I think it's really important to distinguish between thermodynamic entropy where in every physical situation, its meaning is very clear. And informational entropy, for good or bad, the word entropy was stuck to information theory. I think von Neumann was responsible for this.
Yes.
Shannon was asking for a word to describe this information that was talking about, and pi log pi. And von Neumann apparently told him, well, call it entropy. Nobody understands it anyway. So
Yeah.
I think one of the things that, for my own clarity, if there is a concept of temperature, that's physical entropy. If somebody is talking about entropy of DNA or this or that, I said, what temperature are you talking about? Or entropy of words in a book or message. There's no concept of temperature. Thermodynamic entropy always has a concept of temperature.
I have to say something here now, because I have this problem every time I talk to physicists and I talk about entropy and they say, where is your coupling parameter? There's no coupling parameter. Our problem is that right now we're probably still in the embryonic stages of understanding what thermodynamics is and even what information theory is. And we're using interchangeably terms that are finally different from each other. In fact, if we are talking about Boltzmann entropy, Gibbs energy, Shannon entropy, and whoever's entropy, and we do not know what they mean, we're already set up for confusion. In fact, James has a whole paper where he goes about this. If we don't know what we mean by entropy, we cannot talk about paradoxes. I mean, a paradox is, for most time, a paradox is an ill-defined problem that, you know, confuses the solution. So you talk about temperature. In my view of entropy, I take Shannon's view. I don't know what you want to call it. We can call it Shannon's entropy. We can call it H. It's not thermodynamic entropy, and it's equal to thermodynamic entropy under certain conditions. So Shannon's H applies to any distribution, You flip a coin, it has an entropy. You choose your tie tomorrow with some probability, it has an entropy. This is not what the physicist would measure in the lab.
I have a comment. Can I say something just quickly? I mean, I wonder if the connection here isn't that information is just not amorphous. It needs to have a medium in order to be stored, communicated, and otherwise transferred. And so if you look at it in that sort of a context, temperature then becomes relevant because the medium itself is temperature stable or unstable. And this is the connection, I think, between temperature and the bit of information that can flip very quickly or effectively be dissipated depending on the temperature of the medium. So I think there may be a connection here that we're missing.
Yeah, if I can say a few words, it's not so much information that stands by itself. If you look at, there's a common thread and theme, if you will, between what I think of thermodynamic entropy, Shannon entropy, and something that arises in controls or feedback systems, and that's the Bode integrals. And they're all fundamental limits of performance. Basically, the thermodynamic entropy tells you something about the fundamental limits of performance of a heat engine, whereas the Bode integrals, coupled with the Shannon entropy, which is basically information or measurements that you use in feedback systems, tells you how much performance you're able to get out of a feedback system, a closed loop system. So the underlying thread here is actually limits of performance. So there is a connection there.
Because all of this is based on a variational principle. We're maximizing something. What it is we're maximizing. In my view, we're maximizing the probability of the probability distribution. If things could happen with this probability or that probability, where a maximization is by definition a variational problem. It sets a limit. Talking back to temperature, to me temperature has a very simple meaning independently of molecules. It has to do with the choosiness. If you have n microstates at infinite temperature, they're equally probable. That's what statistical mechanics says. Temperature is infinite, all of those are equally probable. And as you decrease temperature, you become more choosy. You choose the lower energy with higher and higher probability. And at zero temperature, you only pick the lowest energy. So temperature is nothing else but choosiness. In physics, it's coupled, it arises from intermolecular forces. But when I choose my necktie, it has to do with, if I'm in a hurry to get something, it's infinite temperature. I will pick the first tie and run out of the house.
Yeah.
If it's important for me to look really good because I'm talking to a conference. Like
That's
that.
really great.
I just want to point out just one comment. When people actually measure temperature, all this probability stuff doesn't even come into play. We just stick a thermometer and measure temperature, and they give interpretations. And I want to point out that when the concept of entropy was formulated, it is entirely macroscopic. And you don't need any of these macroscopic things. Statistical mechanics is very useful for deriving equations of state. But you can do all of thermodynamics without ever talking about statistical mechanics. That is why Einstein pointed out that it is an independent subject with all the conclusions coming from the two laws. So
I think that's great ending with what Dilip. I think that's a great time to end this today. And before going for the next day, I just want to remind you all, tomorrow we are starting at 8:30 sharp. Therefore, I'll request all to join at least at 8:15. And I request chair of that session, Carl Abel, to be there as well. I think I saw Carl Abel here. And before concluding the day today, I would like to thank my colleague, especially Christine Tang, Anvit Adhikari, Garvin Boyle, and Rajendra Adhikari, who has worked behind the scene tirelessly to make all this happen. And with that, permit me to conclude the session today, and we'll meet tomorrow and continue this great discussion. Thank you so much all.
And thank you, Ram.
Thank you.
For organizing all this. I think
You've done
you
a
did a
terrific
fantastic
job.
job.
Thank you, Ram.
Thank you.
Thank
Thank
you.
you. Thank you.
Bye-bye.
Thank you, Terry.